Hello, welcome to our last lecture. I just want to show I'm very proud of being South African with a Bulgarian background. I'm born in Bulgaria, but I'm South African now with Bulgarian origin, and this is the place where I live. This is the beach. I'm very proud that I live in the best place of the earth, South Africa, with this beautiful south coast, which has eternal summer all around, and the summer is not so hot and the winter is not so cold, and had a beautiful weather. And I live near the coast, as you know. So this is going to be our final lecture, and this is why I dressed in my traditional outfit, my Zulu outfit, to show my pride of being South African. And I'd like we to delve into the final stages of our lectures. Let's start with something that is actually very, very tragic, and that is the tragedy which happened in the Lake Nyos in the Cameroon. And this tragedy happens in 1986, which again confirms another chemistry law, and this chemistry law should have been known to prevent this loss of life of 10,000 people. This is Lake Nyos, how it looks now. But what happened in 1996? The Lake Nyos gets very concentrated deposit of carbon dioxide, and because carbon dioxide gets dissolved easier in the cold water, it gets deposited down in the lake, and gets more and more deposited. I don't know what's the sources of that exactly, but now something else happened, and this something else makes, maybe it was an earthquake, I don't know what it was happened, but it was a disruption, and the carbon dioxide actually bubbles up, went up, and carbon dioxide, there is no color, there is no smell, there is no flavor, there is nothing. You can't taste it, you can't smell it, you can't see it, and because it's heavier than the air, it's actually a war poison. Actually, you can do it. It went down from this place. It went down the hills and killed 10,000 people. Some of them in their sleep even, right? Cattle and human being. So why this happening? Why this is happening? It's simply because the solubility of the gas, because maybe there was a temperature difference. If there is a rising the temperature, the gas is gonna get released. You can make this experiment yourself at home. Take a Diet Coke and open it, and take a paper, make it like a roll, and put there inside 7 Mentos or 8 Mentos. It mustn't be less than 7 Mentos. And when you put them into the bottle, run away, because you're gonna have 3 meters high explosion. Why this is happening? Because the Mentos has a very particular structure which makes a creation point of the bubbles of the carbon dioxide, which is in Coke. And because it's heavier than the Coke, it goes down to the bottom and creates these bubbles of this rough structure. And then after, all of these bubbles come immediately and blow up all the liquid. All right, just stay away. And you can do it in the house of your mother-in-law, or maybe your ex, but don't do it at home. Do it somewhere far, unless you wanna travel. And the laws that we studied, that the solubility is increased by the lowering the temperature, and the Henry law, the concentration of the gas depends on the partial pressure above the gas of the solute gas. Now then I need to ask you a question, practical question. Before a carbonated beverage bottle is sealed, like the Coke, it's sealed, otherwise it's not going to when you open it. it's pressurized mixture of carbon dioxide and air. Now, can you explain me why there is start bubbling when you opening it? Why? That first. And second, I want you to explain me what causes the fog when you opening it. You can see there is a little fog which causes this. All of this we studied. Give me answer, please. Yes, if you answer this, you are right. First thing, when you open, because it was sealed with more pressure to keep the carbon dioxide inside, it was more pressure. So now when you open it, you make the pressure equal to the atmospheric, and now you've got less pressure. According to Henry's law, less pressure, less solubility, less concentration of the gas. So now the gas goes out, and this is why it starts fizzing. But now why this fog, little fog you can see for a moment? The gas expands because it's more pressure, and as I said, when the gas expands, his kinetic energy gets loosed by pushing the atmosphere. And because it loses his kinetic energy, you tell me when the kinetic energy is lost, the temperature falls down. Davis experiment. Moving of the molecules makes the temperature. So you've got moving, they lost their, they do work, they lose their kinetic energy and lose their temperature. This is why there is a low temperature there, and when you got low temperature, the water vapor, which is in the coke and the air, start turned into a small water droplets, right? Because we're lowering the temperature. And now when it's lowered, you've got small water droplets, and then you've got this fog then on the top of it. Then my second exercise and my second question, miner works 300 meters underground, works, and his wife gave him a carbonated drink, Coke or whatever you want to say. When it gave him his carbonated drink, he said, no, it's too hot now, I want to drink. Definitely 300 meters under the ground is hotter than outside. So he opened the drink, he started drinking and says, man, how can produce such a plain carbonated drink? It's not bubbles there, it's nothing. Actually, bubbles didn't come, there is nothing. Why, you know, the bubbles didn't come, why it wasn't fuzzy? It was bland. And, you know, it's like a flat. There is no bubbles. It wasn't carbonated. Now, after drinking it, he took the elevator and started going up with his colleagues. Hey, this man start burping, man. And start belching all around. All the people says, hey, man, you don't have manners here. I says, no, man, sorry, I can't keep it, man. Why start burping and why start all of this belching, you know, why? And why the cold drink was flat and non-fuzzy when it opened at 300 meters. Yeah. Why? Okay, let me explain you why. It's very simple. If you know Henry's law, you'll answer it. First thing, when you got more pressure, you've got more solubility of the gas. So that means 300 meters down on under the ground, you've got more pressure. It's not like the atmospheric pressure at the surface. You've got more pressure down. So now that pressure pushes down, so the gas is not it's not gonna, it makes actually the gas more soluble. So the gas stays into the solvent. So the carbon dioxide, because of the pressure, stays there in the drink. This is why it's bland. It's not get fizzed out when as you opening the other one, which was pressure. As you see, when you buy the Coke from the shop, it doesn't fizz because it has pressure on the top. According to the Henry law, more pressure, more solubility of gas. So you've got more pressure down on the mine, you've got more solubility. This is why you don't have bubbles. But now why start burping? You tell me. Now the pressure gets up, but the liquid is in his stomach. And still you've got more concentrated carbon dioxide in that carbonated drink. Yeah, but it's still in his stomach. So now when you've got less pressure, now because it's getting up now to the to the ground, no, not under the ground. Now the carbon dioxide, which is dissolved according to the Henry law, is going to have less dissolved because the pressure is less, and you know the Henry law says less pressure, less concentration of the gas into the solution. So now the gas bubbles start coming out, and this is why I start burping. You can't even stop it. So it's not question of bad manners; it's a question of chemistry. All right. So this is regarding the solubility of water and the gases. Now we need to go into another quality of water, which is amphoteric. What is amphoteric? Amphoteric means that the water acts as acid and as a base at the same time. That's the only substance that does that. Look, there is ionic substances like a sulfuric ion, sulfate ion, but that's different, which is that's not neutral. This is a neutral substance, water, and is both acid and both base. Now what you're looking here is that you've got nitrous acid, and then you've got water, which act as a base, and then turns to the reaction, which actually makes it the water acts as a base when you put nitrous acid. Now when you put a base like ammonia, then the water acts like an acid. You see, in one case is the base, in other cases acid, and this is what's called amphoteric, meaning that it can act as both as an acid as a base. Is crucial for many biological and chemical processes. The dual behavior of this water allows water to participate in a wide range of reactions, including that regulate the pH. Otherwise, if our pH gets too high, we die. If it's too low, we also die. If it gets too acidic, we got acidosis, death. All right. And also not only regulating the pH, but also transport protons, facilitate essential actually biochemical reactions. With the pH regulation, it will maintain stable pH levels in the biological systems and chemical solutions. It can neutralize acids and bases and preventing these drastic changes that could disrupt biological process and kills us actually. Also proton transfer we've got, and this proton transfer is because the water readily accepts or donates protons. That means hydrogen ions. When the hydrogen gets ionized, you've got only one proton left, which is essential for many also chemical reactions. This ability to act as a proton shuttle is vital in the enzyme catalysis, cellular replication, and other biochemical pathways. When we say enzymes, I just want to ask you again, why when the water, carbonated water or a Coke, gets into your mouth, you can see that immediately gets a lot of bubbles, gets sometimes even out of your nose, goes to your sinuses. Oh, it's too much carbonated. Ah, man. Why it's like this? When it stays in the glass, it's one thing, but when you put it in your mouth, first thing your mouth is warmer. Depends on the temperature. More temperature, it bubbles out. Second, you've got carbonic anhydrase enzyme. Enzyme is a biological catalyst. It actually speeds up biological processes. So you've got carbonic anhydrase in your mouth, which actually releases the carbon dioxide even much faster. Carbonic anhydrase is actually responsible for transferring the carbon dioxide out of your muscles, out of your cells, to the lungs and to be exhaled. Otherwise you'll die. So we need this enzyme to throw it out, the carbon dioxide. And the carbon dioxide is a result of metabolic process. When you got glucose, it gets into water and carbon dioxide. Carbon dioxide cannot stay in your body. It's going to poison. You have to be thrown out. You have to be exhaled. And this is why we've got carbonic anhydrase, which takes it from the your cells through the blood, takes it with your veins into the lungs, and with the veins, because of the different partial pressure, we've got more carbon dioxide than the air. It gets from the blood, bubbles out, and goes into the air, and you exhale. Every moment you exhale, you do this process. Henry's law. See, that's not chemistry. Now, another dangerous thing is radiation, which is actually all around, and we need to be aware of this radiation. So, what's happening with the radiation? Look at it now. It's actually very, very dangerous. You've got this structure of water. That's a water, right? You've got oxygen, and you've got hydrogen. There is a water molecule, and you've got ionizing radiation, and knocks out one of the electrons, because the ionizing radiation is with very high energy, and when it knocks out this electron, it doesn't return back like we saw before with other radiation types, like different colors of radiations which we tried. But now what's happening is this one becomes ionized. The water becomes ionized. And what is happening is the water first forms this cation, because now the water was neutral, but now it's not a neutral. Now it becomes it becomes positive because we knocked one electron. When you knocked one electron, the water molecule, now it becomes cation. And this is radical. Radical is something that has unpaired electrons. And in this case, you can see it here. You've got unpaired electron. And this unpaired electron is not very happy staying alone, so try to get connected and gets very reactive. So now you've got this radical cation, and you've got one electron released. And the human body is composed largely of water, 60 to 80% water. And water molecules are the most abundant molecules in your body. And when there is a abundant ionizable targets like the water, and our cells, which are full of water, and when the ionizing radiation comes, it hits them, and it creates this cation radical. And what's happening after now is that the molecules in the body, it reacts with the water molecules in the body to create a hydronium ion, H3O plus, or normally it's written H plus. You can see it in different places different. And that's the most dangerous thing, is hydroxyl free radical. Look at that picture now. That's the most dangerous thing. The water, when it reacts with hydroxyl cation, it creates this radical. I said radical is something that has unpaired electrons, and this hydroxyl radical, don't confuse it with hydroxyl ion. Must be clear distinction. Hydroxyl radical is has one or more unpaired electrons, right? The hydroxyl ion doesn't have any unpaired electrons. All electrons are bonded together, just negative charge. Makes it also reactive, but not so reactive, the one with the unpaired electrons. The electron that is unpaired, which is radical, so I call the free radicals, are very dangerous to your body. It actually damages your DNA. So what's happening here, the hydroxyl radicals are very reactive because of course of this unpaired electron which is there. It's written like this, not with minus, to confuse it with hydroxyl ion. And they readily attack other molecules, right? Together with oxygen, which is also very reactive, and to achieve stability, because they are chemically unstable. This one electron in the radical must be connected. So radical cations are also reactive, but not like this hydroxyl radical. So now this ionizing radiation, when it comes with your body, with water, generates this hydroxyl radical, and enhances the injury of the cell and of the DNA, damages the DNA, and the DNA must be replicated. Otherwise, you're gonna die if your DNA is not replicated. Different structures in your body get replicated with different speed. Your bones can be for years, your skin for days, and your lining of your stomach also for days. And when it damages that, the DNA, the DNA comes with a mistake in the structure, and when there is a mistake, it's a cancer. So when the oxygen is also very reactive in this case, and actually enhances this damaging of the cells and all this lipid membranes, mitochondria, you name it, it's just terrible. Thank you very much for being faithfully throughout all the lectures. I hope you enjoyed them. I hope that they will enhance your life, and I'd like to encourage you further to go into study of more this, and one day maybe I'm going to listen to your lectures. I study every day, though I don't need to. I don't prepare for anything else. I study every day. It's just the process of studying makes me very happy, and makes me seeing God's law and God's protection and God's care for our world and for us. And actually, I can see the finger of God all around. And that's a very incredible thing, which it's worth studying. And we're going to study of this throughout all eternity when Jesus comes and takes us. And my desire is to start our study here and continuing it, because like Copernicus says, the knowledge is endless like the universe. And then we're going to increase our knowledge with more and more things that actually we didn't know that they exist. And let this be one of the first steps towards that noble and sublime goal. And may God bless you, and I wish you all the best for you and your family, and thank you for watching it.